These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optic series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state or province, and country. Thanks, and enjoy the podcasts. This is a discussion about mirrors, and mirrors are not complicated. It's really, mirrors are a kind of one-trick pony. You just need to learn one thing, and the rest of mirrors will be very, very easy, easier than even lenses. And the one thing that you have to learn is that mirrors mirror things. They mirror light, and they mirror our conventions. So before rays of light that are destined to strike a mirror strike the mirror, our conventions are as they always are. And after they hit the mirror, our conventions are mirrored. So let's take the case of this. This is an object. Okay? Is the object real or virtual? This is a real object. It's to the left of the mirror. The rays of light hit the mirror and bounce off the mirror. And I extrapolate these rays of light back to here, to our image. Is the image real or virtual? Since these are rays of light that have hit the mirror, our conventions are mirrored. In this case, an image to the right of a mirror is virtual. So an object to the left of a mirror is real, an image to the left of a mirror is real. An image, or for that matter, an object to the right of a mirror are virtual. Now here is a question that we're often asked, and is a sort of a fun problem. How tall does a full-length mirror have to be? So let's say that we have some twins here, and they're going off to their senior prom, and they look at each other through a window. And my question is, how tall does the window have to be for twin on the left to see the shoes of twin on the right? And I'm giving you as a given that they are equidistant from that window. So the twin on the left is however many meters he is from the window. That's how far twin on the right is from the window too. And I think that you can pretty clearly see that the window need only be half the height of the person. Half, because this is triangle number 1, and the base of triangle number 2 is twice what triangle number 1 is. Therefore, this height is only half of this height. Now, if we take the window and we substitute a mirror for it, we see that the identical situation applies. And in fact, we're going to drop the second twin out. And we can see that a mirror need only be half the height of the person looking into it in order for it to be a full-length mirror, in order for him to see his full height. Now, what is the thing I did not specify? I did not specify the distance of this gentleman from the mirror. That means that this calculation is independent of distance. If he steps back, he won't see any more of himself, and if he steps forward, he won't see any less. And in fact, you can try this out with a hand mirror, as long as it's a zero-power hand mirror, a non-magnifying hand mirror, that you can see a portion of yourself. Let's say that you can see from the top of your head to midway down on your chest through the mirror. If you push the mirror back, you will not see any more of yourself. And if you bring the mirror towards you, you will not see any less of yourself. So that's counterintuitive, but it's true. Full-length mirror, half height of the person. Okay. Let's take the case of a convex mirror here. Now, like everything else with mirrors, our conventions are mirrored. Convex means minus with a mirror. Convex meant plus with a lens. So let's take our primary and secondary focal points. Now, the primary focal point is the point from which rays of light emanating and striking the, in this case, mirror, will emerge from the mirror with a zero divergence. In order to do that, we need rays of light to be coming in to this minus mirror with a plus divergence, and that's shown here. And we extrapolate them backwards and we say, well, the primary focal point must be here. Now, where's the secondary focal point? Secondary focal point is formed when parallel rays of light strike the mirror, and when those rays of light emerge, where they converge is where the secondary focal point is. So it's zero divergence rays of light coming in, and the secondary focal point is here. So the secondary focal point and the primary focal point for the mirror are in the same place. So with mirrors, we don't talk about primary and secondary focal points. We only talk about the focal point. So it's very, very, very easy. Okay. This is a cross-section through a plus mirror, which is concave. And again, the primary and secondary focal point are in the same place. Now, let's talk about the power of a mirror. I'm going to kind of work it through stepwise because I think it's kind of neat. I've drawn here a radius. It's as if we were inside of a silvered sphere, right in the center of the sphere, and we shine a light against the inside surface of the sphere. Well, if we're really in the center, anywhere that we shine it, we will strike the surface of the lens perpendicularly. So that if we have a bunch of rays of light starting out from the center of this mirror, they will all bounce back to the same place, to the center. Meaning that if we put an object in the center, the image will be formed in the center too. Now, you remember the object image displacement problems that we did when we did conjugate planes. When we said if you move an object to the left, an image moves to the left, not necessarily at the same rate. With a mirror, if we move an object to the left, the image moves to the right. And when we work with mirror powers later on, you can solve this as a divergence problem. It's not difficult. What we're going to do is we're going to take our object and we're going to move it to the left. And the image is going to move to the right, closer to the inside surface of the mirror. We're going to take our object from here, from the center, and move it to the left. And our image is going to start to move to the right. We're going to take our object and we're going to move it all the way out to infinity on the left. And where the image winds up being just about here at r over 2. So f for this mirror is going to be equal to r over 2. The dioptric power of this mirror, therefore, is going to be equal to 2 over r. Retake from here. The dioptric power of this lens is going to be equal to 2 over r. And the nice thing with this calculation is that there's no n. We don't worry about what the index of refraction of the mirror is or what the mirror's in. It's very easy. It is just 2 over r. The cornea is a bunch of things. The cornea has a net refracting power of plus 45-ish. And it has that because the index of refraction of the medium on the inside of the cornea is higher than the index of refraction of the medium on the outside of the cornea. And I say that because if you were to excise a corneal button and hold it up in air, that button would be thinner centrally than it is in the periphery. And you know that the central cornea is thinner than the peripheral cornea is. Well, you know, that means it's a minus lens. So if the cornea had air on both sides, it would actually act as a minus lens. Unimportant for vision, the cornea also acts as a mirror. And because problems dealing with the cornea as a mirror are so common, and because the numbers given are always the same numbers, we're just going to solve this problem and you can just memorize what the answer is. Let's say that we have a cornea with a radius of curvature of 8 millimeters. What is the power of the cornea as a mirror, as a reflecting surface? The power is equal to 2 over r. In this case, it's 2 over 0.008, which is 250 diopters. We see that the cornea is convex, therefore it must be a minus mirror. So the reflecting power of the cornea is minus 250 diopters.